All right, any questions, you guys? Any questions? So last time we were here, somewhere here, I think we covered all the pipeline for pre-processing, if I recall correctly. Yeah, so I think this is what we did, correct? So we completed our pre-processing pipeline last time. You guys remember that? And then we did like putting it all together, where I opened up an app and showed you how you put all of these things together, where you load the data and create your pipeline and run it through, and you get your results, and then you dump it, save it into a pickle file, correct? Where that would have your whole data set, correct? The train and test sets, correct? You guys remember that? So what we want to do today is, so what's the next step in this process? So what we've done up to this point is we've examined our data. We've identified some features that we want to add, so feature engineered. We pre-processed the data. If there was any kind of normalization that we had to do, we did. If we had to convert features to one-hot encoding, categorical features, we did all of that. We built all of that as part of this pipeline, and at the end of this process, we have data set to work with, correct? We haven't developed any machine learning models yet, correct? Just the data, all of this, okay? So the next thing we want to do is we want to build our models. The good news is that we've already done a lot of that, so that should not take that much of a time. But what I want to do is I want to bring your attention to the amount of energy and time spent in getting the data ready. And that's usually what you'll end up doing, correct? Because the modeling part, once you understand what the modeling part is, it applies the same to anything, as long as you have that data properly to put together, correct? So now, what is the process? So what do we do now that we have the data, and it's all ready to go, we feel like we've added the features, we normalized, we did what we needed to do, it's ready to be used. What do we do next? So the next step in the process is to kind of play around. And you play around by asking which of these machine learning modeling tools work best on this data set. Now remember when we started, I said, I can't tell you, here's a data set, go use linear regression on this, that's the best model to use, correct? I don't have no idea what model works best, even at this stage, correct? Now when we get later on in the course where we talk about deep neural networks or DNNs, you will see that some of what we've done may not be necessary, correct? But a lot of people still do quite a bit of pre-processing of the data and trying to play around. So for now, what we're going to do is going to say, okay, let's see what we're going to do. We're going to take our data and we're going to ask ourselves, do we do validation or do we do cross-validation? So a simple answer to your question, if you're not concerned about the amount of data you have, that means you've got a lot of data. And if you're not concerned about computational complexity, you have good processors and you can run them, cross-validation is your best. Okay? Now, if you don't have a lot of data, let's say you've got, so if you don't have a lot of data, cross-validation would work, correct? But if you've got a lot of data, then you might say, I might want to go to a validation model because I'm not going to lose anything by taking 10% out. And what it buys you time. And time would be because if you think of like tenfold cross-validation, you build the 10 separate models through that process, correct? And then you kind of figure out what's the best or average them or whatever it is, correct? You guys are following this? So it buys you time. But if you have the data and you've got computational power, just do cross-validation. A good common fold would be 10, often use tenfold cross-validation, but you be the judge of that, okay? So here's an example. Let's say that you've got 100 data points and you've got a lot of features. That's all you have, correct? So if you do a tenfold cross-validation, you're throwing away 10% of your data, 10 out of 100, correct? That's a big chunk of data to throw away, correct? Given that the small amount of, so in this case, you might want to say, no, you know what? I'm going to increase my fold. So I will, for example, train on 99 data points and test on 1. And I'll repeat this. And that way you maximize the number of data points that you have for training, correct? On the other hand, if you've got thousands of data points, You might do a 10-fold cross-validation, correct, or 20-fold cross-validation. It's all balanced between how much data you have and how much time you have in terms of computing resources, okay? So now, statistically, if you've got, and I want to be very careful about saying this, because if there's a statistician that will bark at me, we say at least 30 data points, but it really depends on the size of the features, this number of features, correct? There's a concept called curse of dimensionality. What that really means is that if you have 10 data points, and if you put those on a line, they're pretty close to each other. If you take those 10 data points and throw them into a square, they're going to be more sparse. If you put them in a cube, and as you increase the dimensionality of the problem, these data points could be so far apart that really doesn't occupy the space for you to do anything good. The only luck you have is if these data points are clustered in a way where you could use high-end machine learning tools to identify those clusters in this hyper cloud of data. Correct? You guys are following what I'm saying here? Okay. But I just say 30 is roughly what you want. You don't want to go below that, correct? But it very much is feature dependent. Okay. Let's see here. Let's move on. So let's stick with cross-validation. That's what we're going to do. Stick with cross-validation. Let me push this to full screen here. Let's go with cross-validation. So how would you do cross-validation? Now, you could do it yourself, correct? You could create a loop, cut your data set into 10 chunks, grab 9 chunks, train, test, validate on 1 chunk, and repeat for all these possibilities, correct? You could also use this cross-val method, cross-val score method that comes with scikit-learn. And what you do here is it really is a very nice tool that does it for you. You give it the model. So you first create a model, say linear reg equals to linear regression. That's a reference to an object, okay, a model object. Then you follow it by giving it the training set, in this case X-train process, which would be all of our features, correct? And then you give it the Y-train. You give it a scoring. So you have to tell it how you want it to score as it does the cross-validation. So in this case, we'd say mean squared error. Now, do you see that neg_neg, mean squared error? Now, this method, cross-val scores, does a maximization. Okay, so instead of minimization, it doesn't matter, correct? It just flips things around, correct? So the scores that you're going to get back are going to be negatives. All you have to do is just multiply them by -1, you get the scores back, correct? Just keep that in mind. Okay, are you guys following this? And then CV equals to 10 basically says how many folds, correct? So we want to do 10-fold cross-validation using a linear regression model given this training set and test set, the X-train and Y-train that I provided, and I want to get mean squared error, correct? Now note that this is mean squared error, which means sum of the squares of error over the number of samples, correct? You guys are good? Okay, and what this is going to do is going to take your X-train, Y-train, and it's going to chop it up into 10 chunks and does all of those things for you and give you the scores back for every experiment. So it gives you 10 scores back. Okay? So let's do this. So the way you work it is, so first you have to get it. So it's from model selection. You bring in cross-val score. This is your old standard linear regression. We build the object. Linear reg equals to linear regression. We say cross-val score. We give it linear regression, train Y, this and that, and we get the scores back. If I print those scores that I just got back from cross-validation, so this is going to train all of those things, test it for you, validate it for you, and give you the validation scores back, you're going to get this. And if you note in here, you've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So on fold 1, you got minus 4.95 times 10 to the power of 9. This is, remember, this is squared errors, okay? So error squared. And then if you look at the 10th fold or the last fold, that would be minus 4.94 times 10 to the power of 9. Okay, that's your score on that one. Now, I kind of like to do a few other things. First of all, I want to get root mean squared error because mean squared error are usually very large, correct? And it wouldn't give me a feel as to where I stand with respect to my data points, correct? So I take the square root of that. So root mean squared error, and I multiply by negative, correct? So I convert these to positive right there. square root of the negative of these scores, correct? And I get that back, and that would be my RMSE, or root mean squared errors. Okay. Now these numbers are a little, I don't understand them, because I can't kind of tell where they stand, correct? So the other thing we can do is just to get a feel for the whole, all of these models, you get the average of all of those, correct? And so that would be the mean of those scores. So let's see here, linear RMSE scores dot mean, correct? You get the average all of those 10 runs together, and that would be your root mean squared error for all the validations. So that's called an average validation score, cross-validation score. Okay, you guys are with me so far? Yes? Okay. So once I have that, the next thing I want to do is, so that error is very relative, correct? So for example, if my housing prices are in the range of 0 to 500,000, and I'm getting about what, $7,000 up and down in price, I might have a good model, correct? So instead of 575, it predicts 500. I might say that I have a good model. So to kind of get a feel for where the model is, what we want to do is we want to normalize these results, the errors that are coming back to you, because they're root mean squared error, to the range of the values of y. And once you normalize it to that, it gives you something that's more easier to look at. It's a percentage you could think of. Okay? So to get the range of y, so you take y train max minus y train min, call it target range, and just divide what you have by the target range. So take your average cross-validation linear RMSE and divide it by target range, and that should come up with a percentage. And you could write it as a percentage, 14.17%. So the error here is, roughly speaking, is 14.17%. Does that make sense? Are you guys following this? What's acceptable? You decide. Or maybe whoever gives you the problem decides. I have a tolerance. If I'm predicting housing prices, I have a tolerance of 5% above or below. Otherwise, I'm going to lose money because I'm insuring these properties, correct? So it's them that tell you. And then when you do all of these things, at the end, you're going to run the test on that and see where you stand. Remember, these are all validation errors now, correct? We don't have the test errors yet. It's all validation. Okay? That's the last thing you do, and that's what you report. You say, here's a model. After doing all of this, it validates, well, the test results is this, and this is what you get as an average, as a score for that. Okay? Everybody's good with this? Okay? So now, what we have kind of done, we've learned how to do cross-validation on a linear regression, correct? This was just kind of getting to this and reporting it in a percentage way. The next thing we want to do is we want to train a whole bunch of models. So we want to grab a whole variety of models. We want to get, for example, linear regression. We want to get ridge regression, elastic nets. We want to get a few other models. And as we move on through this course, all the other models that I introduced, you might want to grab those and run them through the data set. Now, if the data set is very large, you might just grab a subset, because this is your preliminary examination, correct? You're just trying to find a model that's better than all the other ones on that. So if you've got millions of data points, just grab 10% of them and do this step. So this step doesn't have to be done on all the data set unless the data set is small enough that this would run quickly, correct? Are you guys following this? This step is referred to as model selection. Your goal is to find the model that best performs on this data set. And generally speaking, at this stage, we just use default hyperparameters. We don't worry about tuning of hyperparameters, correct? Because the defaults are generally the good place to start with anyway. So what we're saying is, if I use these 5 models with their default hyperparameters, which one does better in validating with this data? Okay, you guys following this? We'll kind of plot those, compare. Okay, this is the one we're going to pick. Now that you picked that one, now you're going to go ahead and mess around with hyperparameters of that model, fine-tuning that model to the data using validation, correct? Are you guys following? So let's say I use those 4 things that you already know, correct? Linear regression, ridge regression, elastic net, and the other one. Okay, you guys are with me here? And then I came up with running all of this, and one came with 10% average cross validation, the other one came with 3%, That one came with 12%, and I say, okay, the 3% one is the one that I'm going to pick. And then now you take that 3% one, and you ask yourself, what are the most important hyperparameters? And you first start with those most important hyperparameters. For example, learning rate is your number one you should always play around with. And what you do is you just, I'll show you soon, is you create a grid search, you automate the process, and you let the system loose. It goes through and grabs, boom, 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 runs all of these experiments and come back and tells you these set of hyperparameters are the best set of hyperparameters to use by experimenting through cross-validation. And at that point, you have your model, you select it, you run your test. You guys with me? So let's do it. Let's go for it. I'm going to introduce you to a couple other models. And as you go forward in your assignment, I'm asking you for you to go and explore another model. Just remember, when you learn how to use one model, you know how to use all the other models. The only thing that changes is their hyperparameters and maybe learning a little bit about them in terms of understanding what they do. Okay? So we're going to do this by exploring these models. We're going to use linear regression. We're going to create a second-degree polynomial and test it on that. We're going to do a ridge regression on this second-degree polynomial. We're going to do a lasso on this second-degree polynomial. We're going to do elastic net on the second-degree polynomial. We're going to create a decision tree regressor, and we're going to do a random forest regression. Now, I'm going to talk about this, but these are two powerful tools in terms of doing some amount of nonlinear, non-parametric work. And then we'll expand in other dimensions, correct? The other tools. So let's take a look at this. So first, how do you use a linear regression model? Well, you just look it up. You say from sklearn, grab decision tree regressor. You just create the object, and you're good to go. Remember, this is our default parameter, correct? That's all we need to do is create the object. You don't need to provide any hyperparameters. You don't even need to know what does that mean. Later you need to know, because if this was your best, then you need to dig deep and say, what are my hyperparameters and what do I do with it, correct? Are you guys with me? At this stage, just go grab them and run them. And in this problem, we just have not too much data, so we should be okay to run the whole data set through it. Okay, it still will take a little time, like 20, 30 minutes, but 20, 30 minutes is nothing. Some of these models, if you are not careful, could run for months, depending on what machines you're running. Okay, you guys are with me? Okay, so now, the other one we're going to use is random forest regressor. And all you have to do, again, import random forest regressor and just create an object of that type, and you're good to go. The other ones you already know how to create, correct? We've talked about it throughout the course. Ridge regression model and stuff like that. Okay, so now let's spend a little time. Now, we'll talk about running this whole thing, these models through, but I want to just give you an overview of these two. This is something that it would be your job at this stage to go do a little bit of exploring, okay, to the extent that you understand it. So, and for that purpose, I'm just going to give you enough. I mean, if you look at decision trees, you can get a book on decision trees, and there's a whole field about it, correct? But to the extent that we need it, basically what decision tree does, it takes your variables, and you could tell it how many variables, which features, how many features to use and stuff like that. And what it does, it takes that feature, and it kind of moves things around in terms of your data samples and tries to see where is maximum information by looking at how it reduces standard deviation. So it splits the data set on x1 at some point. So let's say x1 runs from 0 to 5. And it identifies, if I take my data samples and break them, where x1 is either below 7 or after 7, or below 0.7 and after 0.7, that gives me the best standard deviation on each set, at least. And then it breaks it at that point, and then it takes each of those two subsets and does the same thing, and repeats and repeats and repeats. So it comes up with this decision tree, and the way the decision tree used is that if you have a new data point, say at x.82, it takes that data point, compares it to the decision, is x 0.82 greater than or less than 0.173? If it's less than 0.173, it goes this way. Otherwise, it goes that way. So in our case, it's going to go this path. Then it's going to compare it with the next level, and then it's going to compare it to the next one until it leads to a leaf node. And then it takes the classification associated with that leaf node and says, that's the class. Are you guys following me here? And that's basically a decision tree algorithm, the way it operates, correct? So now, what's important to you is kind of get a little bit more. So it is called a non-parametric. It's called a non-parametric models because you don't really know how many parameters you have before you start. So for example, when you build a linear regression model and you have 5 features, you really know you only have 6 parameters, 5 W's and 1 B to work with. In this case, you don't know because it just keeps dividing this up and creating all these additional parameters. So it's referred to as a non-parametric method. And let's see here, overview, as I think I just talked about overview, which is basically try to maximize the depth or the desired standard deviation. Okay, so let's take a look at this. So now the next thing we want to do is we want to look at what are hyperparameters here, because remember, if this becomes a selected model, and you do this after if this was the case, correct? You will see this was not the case, so I decided to kind of go over it. But you do want to know what are your hyperparameters and how do they impact overfitting, bias and variance, because that's what you need to work with all of these. Remember, bias and variance is something that you have to always try to balance, correct? Okay, so basically one of the most important piece of this is the maximum depth. So if you look at maximum depth, basically what you're saying is how deep should I let this go? Okay? Now if this gets too deep, what happens? You'll end up with one sample at each leaf nodes, correct? Becomes overfitting. If you make it too narrow, it is going to have bias because you have not really gotten enough flexibility from the data, correct? I understood that much. Okay? So if you actually looked at and graphed it, it will look like this. If you graph that process, you will see something like this. So this is where your max depth is equal to 2. This is where your max depth is equal to 3. And these are decision boundaries in a sense. In here, anything in here is classified as that, or that's the value of its regression. Then you go to this range, that would be the value, correct? That's your X and that's your Y, correct? That's what you're trying to produce. It's a regression model, correct? Remember that? So the deeper you go, the more it fits the data perfectly. Are you guys following this? The less deep you go, so if you had one layer, it would be just the mean, correct? That would be it, nothing else. So that would be the predicted value. Are you guys following this? Simply the mean of the whole Y values. Okay? And so that's the balance you need to do, this maximum depth. Now there's other ones that you need to be aware of, like min sample splits. So that minimum number of samples a node must have before it splits. So if I go back over here, you see that as you split, so here we had 200 data samples, 156 of them ended up here, 44 ended up in here. So then the question is, should I split this or not? And then there's this min number of samples, correct? After which you don't split, correct? And so that's a hyperparameter in a sense, which just kind of works with the depth. And there's a whole bunch. There's min sample leaves. How many leaves do you have before you stop expanding the tree? And some max values, okay? And generally speaking, if you increase your min values or reduce your max values, you will regularize the model. That means you're penalizing it. You're making it more rigid, okay? As you increase the mins and reduce the maxes, okay? So that's basically something to keep in mind. And that's about it. Now, let's talk about bagging and pulling. So sometimes you will see this is this concept of bagging and pulling is that if I build a model to do something for me, it might not be the best model because I might have not picked the right set of initial parameters, okay, or the way it worked. So alternatively, you might say, you know what, instead of doing that, I build a whole bunch of models on subsets of the data set, especially if I have a lot of data sets, and let them all come up with values, and I decide which one works better. Or I combine them together to come up with a solution. For example, I build a model on this subset of the data set, and it makes a prediction of price being 5,000. This other model I train on another subset of this whole data set, correct? If I have a million data points, I use 100,000 of those to build this model, 100,000 to build this model, and so on and so forth. So this one comes with 50,000, the other one comes with 51,000, the other one comes with 75,000. Then I average all of these, and that would be a much better predictor. So it would remove the variance from your problem. Okay, are you guys following this? And these are referred to an ensembled solution, where you ensemble multiple models into giving you a collective decision. If it's classification, which we're going to talk about soon, you get voting. So if 50 of them voted no, 20 of them voted yes, then the vote would be no. Correct? Are you guys following this? All right. So the way it works is you take your data set, you break it into chunks, you bag them up, and then if you do sampling with replacement, that's called the bootstrap. Now you use bootstrap if you don't have a lot of data. Correct? If your data set is small, you replace. That means you put them back and then you use them again. Another random, shuffle them around and grab another chunk. Correct? If you have a lot of data, you don't use bootstrap. Are you guys following this? You guys are good? Okay? And then you train your models and then you make predictions. So here is an example. So for example, if you take, this is an example of an ensembled model. It's called random forest. Basically, you create a whole bunch of trees. Each of those trees are trained on your subset of the data, correct? You take your data, break it into these chunks, either through oversampling or through replacement or none, or bootstrap or none. And then you build these trees and let each of them come with some sort of either a value, if it's a regressor tree, or a classification, if it's a classification tree. And then in this case, you either average them together or you take a majority vote. Okay, so a random forest, that's basically the idea behind it. You create a forest of trees. That's what it's referred to. That is trained on random samples of the data, hence the term random forest. Okay, are you guys following this? And then you ensemble them together in making the decision. So that's another model that we're going to work with. And let's take a look over here, some hyperparameters. So I've already talked about this. Let's see here, some hyperparameters. Now, basically, it has all the hyperparameters of the decision tree, because a random forest is a whole bunch of decision trees, correct? So you've got all of those, but it has its own, correct? So for example, one is an estimator, so number of estimators. This is basically the size of the forest. How many trees am I having in this forest? Okay, are you guys following this? That's the number of estimators. Max leaf node, this is something that we saw in the decision tree algorithm. So you could have that. Max leaf node is 16. This other ones you'll see here and there, and jobs. This basically refers to how many jobs you dispense to different CPUs. So all of these are really able to be dispersed into multiple processor or GPUs if you want to do them. Okay, and that identifies by the number of jobs, correct? We won't use that for the purpose of this course, but I figured it's good to just throw it here so you guys can see, correct? And what this does, if you have different jobs, if it wants to create these different trees, correct, what it does, it sends some of them to one processor, some of them to another processor, and then it collects them all back. Okay, and that distributes the workload. Okay, now these are pretty expensive in terms of computational costs relatively, because now instead of using one tree, I'm talking about 500 different trees to be built, off of which I'm going to make predictions on the data set. Correct? You guys are following? All right, so now let's take the next step. Let's do it. So the way we do this is we're going to have to bring in our models. So linear model, I'm going to get linear regression. I'm going to get ridge. I'm going to get lasso. I'm going to get elastic net. I'm going to bring in decision tree from sklearn tree. I'm going to bring ensemble. From ensemble, I'm going to bring in random forest. Now, again, I can't teach you all the models that are out there, correct? You should go out there. If you have a problem, let's say you have a problem, you're trying to do something, I would generally go and say what other people did, what worked for them. Because often you'll find that, for example, decision trees are good for this kind of problems. And you want to make sure they're included in this set, correct? And you might come across something I have not talked about or was not even there today, correct? And tomorrow somebody developed it. You want to make sure that you explore all those possibilities, okay? So here we go. And then the next thing we're going to do is, because we're going to do ridge, lasso, and elastic net, what we want to do polynomial features. Now, second degree polynomial. Now, you could do higher degree polynomial. Remember, you guys remember ridge, lasso, and elastic net? They were basically there with regularization, correct? You can't regularize a linear model. It's already regularized, correct? It's a line. So you give it some flexibility, and then you regularize it through those possibilities, okay? So we add those features. So now what I want you to see here is we've got our original features, which is called X-train processed. And we have our poly features, which are X-train processed poly. We will use X-train processed poly, that means our X-train with poly features added, for basically polynomial regression and ridge, lasso, and elastic net. For all the other ones, we use our own, we use the X-train processed, okay? So now, next we have everything we need here. We have the models. Next, what we're going to do is we're going to actually create the models from those. So here it says linear. Can you guys read this? Okay, linear regression equals to linear regression. That's ridge, gives it a regularization value of 0.1, and it says max iteration is 1,000. Then we've got lasso. Then we've got elastic net, decision tree, and random forest. Here's where we use cross-val score. Okay, so you guys remember cross-val score? It would do cross-validation. I give it, for the first one, I give it linear regression, give it the train process, we give it Y-train. I give it the negative mean squared error for our error measure, and we do a CV of 10. Next one, we're going to do for poly scores, and here we're going to use linear regression, but we're going to use the poly features there, so we are basically doing polynomial regression, okay, with no regularization. So X-train process poly, and that would be poly score. And then ridge score, we do cross-validation on linear regression using X-train poly. And let's see here, Y-train, let's see here. Yeah, I made a mistake. This should actually be ridge. My bad. So my bad. This should be, because it's called ridge reg. So we need to do ridge here. So this should be ridge reg. Okay. So anyhow, that's the wrong one. Then we've got a lasso regression on the poly. Then we've got elastic net regressor on the poly. Finally, we're just going to do tree regression and give it X-train process, Y-train process using the same method and cross-validation. You see that same code repeats by having different things. Now, it's not a very clean code. You could have created an array of these functions, just run through a loop going through it, but I didn't have to worry about that. I just wanted to see it. Oh, you guys see it, okay? So we run those things. So this can be easily cleaned up if you wanted to. And then now, guess what? I will take my target range, and I would take my mean squared errors that I got, negate them like we did before, find their square root divided by target range, and each of those will give me a root mean squared error averaged over all the 10 folds, correct? Are you guys with me? And those would be my scores. Next, what I do is I plot them using a bar chart, and you can go back and review your bar charts. And then what I get is I get these as the scores. I look at this and I say, based on these default parameters, it looks like, well, these guys are doing well. Elastic net is close to random forest. And here we go, random forest is right there, seems to be doing the best, correct? You guys are following this? Did I stop that? No, it's going. Okay. Yeah, I didn't want to stop it. So it seems like random forest is the best. Okay, you guys are with me here? Now you might ask yourself here, is that okay? I've got random forest, I've got elastic net. They're pretty close to each other. Elastic net is a lot cheaper to explore than random forest computationally. You might want to first give it a try, correct? Or if you're really picky and you want to get the best, then I would probably just start with random forest. Again, these are decisions you're going to make based on the type of problem you have. Okay? So now, this process that I just went through is referred to as model selection. What we did is we took a whole bunch of models and trained them using the data we had, validate them using tenfold cross-validation, correct? And we did not mess around with hyperparameter. We just used the defaults. Now that we have identified, for example, in this case, random forest is the one that we're going to explore more, then we're going to focus basically grab our magnifying glass and fine-tune those hyperparameters, okay? So this is next. So to do this, there's a couple of functions that you have. And first, let's take a look at this grid search cross-validation. So this comes with scikit-learn. It does this for you, correct? So basically, instead of saying cross-val, you create an object of grid search CV. Basically, what it says, hey, look, and you give it basically a list of dictionaries telling it what hyperparameters and what values of those hyperparameters you want this to search for. And it does all your experiments for you, every single one of them. Okay? So let's take a look at how it's structured. First, we start with something very simple. So the first one, because we're looking at random forest, what you need to do, remember, we're trying to experiment with hyperparameters. You need to kind of identify what are those hyperparameters, correct? You could list them all out. These are all the hyperparameters. And you might do a little bit of research, and you'll find out, like, max features is very important. So you might want to focus your attention on that. You might see other stuff. So for now, let's just go ahead and say, I'm going to experiment with max features. And with max features, I'm going to change from 2 to 4 to 6 to 8. Those are the values of hyperparameters of max features that I want to experiment with. Okay? Now, if you wanted to do it manually, you will do CV cross-val on this with max features set to 2, then set to 4. Or you could automate it using this process. Okay? So the first thing you do is you create a parameter grid, which is a list of dictionary. And for now, we only have one hyperparameter to work with. So this dictionary is composed of one entry, which has the name of the hyperparameter and a list of values that hyperparameter to take on. Okay, are you guys following this? So what I'm saying here is that, you know what? This is the grid. I'm looking at max features as my hyperparameter, and I want to go from 2 to 4 to 6 to 8. Those are the experiments I want to run. Here's the model that I'm going to use, random forest, call it forest regression. And then I create an object of type grid search CV. I give it the model, like I did to the cross-val. I give it the grid param, like we did before, and I give it the folds and the scoring. Everything else remains the same. Instead of saying cross-val, you're just simply saying I want to do a grid search with cross-val using tenfold cross-validation. Next comes fitting. So instead of fitting the cross-val, you fit the grid search. You give it X train process, and you give it Y train. Are you guys following this? And boom, you let go, and when it comes back, you could go ahead and say grid search.best params with underscore, because these are basically the values that it came up with, correct? And it comes back and says, you know what? Max features of 6 was your best parameter in terms of giving you the best average class validation. It does all of that for you, and now you have that, correct? You guys are following this? Boom, you get it. And so now you could do this even more. The beauty of this is it really takes away a lot of headaches and work for you trying to write all these loops in experimental setup and stuff like that. It just does it for you. Okay? So now let's take a look at this. What happens if you wanted to do this? You wanted to run 2 experiments. The first set of experiments you want to run, you wanted to vary max features from 2 to 8. You wanted to vary the number of estimators, the number of trees in the forest from 3, then to 10, then to 30. And you want to set the bootstrap to false. That means you didn't want to resample, correct? So that's basically what you're saying. And experiment 2, you would want to say max features from 2 to 6, num estimators 3 to 10, and bootstraps true and false. You want to try it with and without bootstrap. So first, let's take a look. Looking at that, let's see how many experiments total we're running here. So if you look at max features, which is, how many are these? Are 4. And these are 3. And this is just 1. So it's going to be 4 times 3 times 10. Why 10? 10-fold cross-validation, correct? So every fold requires an experiment, correct? So you're looking at 120 experiments there. And this one, you've got 2, 2, and 2, 8 times 10, which is 80. Add those two up, you're running 170 experiments. Every one of those will develop the model, find its validation errors, and then ultimately adds all of those up in the right. Okay, you guys are following this? Okay, so now, not bad, correct? Not bad, because to do this, I need to just do this. I need to create my grid search. I say bootstrap should be false. Max features should go 2, 4, 6, 8. Num estimators 3, 10, 20. And then I add another dictionary for another experiment, and that would be bootstrap, true, false. Max features 2, 6. Num estimators 3, 10. This part remains intact. Guess what? 6 lines of code runs 170 experiments for you and gives you back what is best. And out of all of those experiments, bootstrap set to false, max features set to 6, and n estimator set to 30 gave you the best results. Boom, you fine-tuned your hyperparameters. You guys good? If you want to dig deep, you can. I won't spend too much time on this. You could actually, so you could look up grid search, and it would tell you things that you could do. For example, you could do grid search CV results underscore. That means cross-validation results. So it keeps everything for you, and you want the mean test score. You could say whatever you want, and will give you back basically all those values. You could even go further. You could say, I want to give all my parameters. So it will give you the parameters and the values. It's kind of messy. Again, I won't go through this. You could use this comprehension here to clean it up. And you could actually say, OK, when bootstrap was false, max features was 2, and estimators was 3. This was the value. So if you want to dig deep and see what were the experiments and what were the results, you can. Questions? Any questions? So now grid search is great because it allows me to systematically go through a grid of hyperparameters and do them, correct? Now, however, it is not always the best approach. Now, if you could think of it, let's just do this. Okay. It's here somewhere. If you could think of it, let's say I've got a data set like this. And I had some data here, and nothing there. And I did this grid search like that. I'll be wasting a lot of time running these experiments, correct? Are you guys following this? So in this kind of scenario where you've got really a large space of a large number of possibilities of those hyperparameters, a random search is better. What random search means is you randomly pick a place in this stop and then run your experiment, correct? So instead of saying go from 2 to 4 to 6 to 8, you basically say, well, you know what? I want to go from 2 to 4 to 6 to 8, but I don't want to go exhaustive. Pick one random from this, pick one random from there, run that experiment, and see what it gets. And what it does a better job in randomizing the location of the search, and you wouldn't miss stuff, correct? So for example, you could also think of it this way. If I ended up searching just here, I will miss those areas that are important, correct? By randomizing, you're basically saying, hey, okay, I'm going to look here, and then I'm going to randomly look there, maybe look there, maybe look there, maybe look there, and so on and so forth, leading to a better solution. And to do this is you just do a random search. Everything remains the same. Everything remains the same. This is actually, let's see here. Oh, where is it? No. Everything remains the same, except instead of doing a grid search CV, you do randomized search CV. Okay, you create your dictionary. Instead of that, you do randomized search CV. But one other parameter you provide is this, which is n iteration, basically saying how many experiments. Because it's random, it no longer, so before we had 170 different experiments. In here I'm saying I don't want to run all the exhaustive search, run 30 random experiments of all 170 possibilities, and let's see where we go. Okay, are you guys following this? That's basically what that is. Any questions? All right, I have this putting it all together. So, oh no, finally, sorry, one last thing you do. Now that we have fine-tuned, we've got our best model, correct? All of that is there. All of that is there. We've identified it. What we do then is we use our best model on our test set, and we get whatever percentage that you get. So now we have 10% error on the test set. Remember, this is the last thing we do. Now, if you want to put all of these codes together, basically, when you look at experimental modeling, right here, you have this code in your demos, so you should be able to run them. So, but I'm just going to go over it. So here's what you're going to see is, basically, remember we saved these in a pickle file, the train and test set. So we load them. We load them from the train and test set using this load housing data, and we open the pickle file and grab the test and train from it. Okay, train set and test set. Next thing we're going to do is we're going to break it up into basically X and Y. So X train and Y train, X test and Y test. Okay, you guys remember these, correct? That's the next thing we do. Then we're going to create our models. We're going to cross-validate our models. This is model selection, just right there. And what we're going to do is we're going to then plot them, pick our model, found that's random forest, then do your grid search or randomized search, find your best model and run it on the test set, and boom, you've got your test set. Okay? Kind of a package, all of these things that we discussed up to now into just one file, and it's what? Not that many lines to begin with, correct? Once you have it all together. So now you have the whole pipeline of machine learning. In fact, today, I should have if I would have given you a project to do for the course, which I should have now that I go back and think about it. I had Riley stop by. He took the course last year, and they were complaining about the project, but he stopped by and says, no, I liked the project, but I was complaining about something else about not being clear. So I'll probably bring it back next year. But this would be where you had everything in your basket to do what you need to do, okay? Because this is the full pipeline, okay? What we're going to do next is we're going to look at a few things. First, we're going to talk about classification, because everything we've talked about is regression. So there's a few things that changes when you do classification. We're going to narrow our focus on classification a little bit. Once we have the classification, then we're going to start looking at more recent, modern machine learning tools. Okay? Questions? Are you guys good? All right, let's go. Let me close this, and I think I can close this one now. And let's see if I can find this one. All right. All right, so classification, what does that mean? Now, up to now, your target was a constant value, a continuous value, correct? You were trying to predict a value. Here, you're trying to predict a class, a label, okay? Now, we have binary classification and multi-class classification. We're going to talk about both of those. So binary classification is the simplest case, and that is you only have two classes. Either you're positive or not. For example, if you're predicting whether there's cancer or not, it's either yay or nay. There's no other alternative, correct? And it's represented by those two values, 0 and 1, 0 representing negative and 1 representing the positive class. And those terms are often used, negative versus positive. Okay, are you guys following this? Okay. And then the multi-class, you actually have labels. So, for example, it could be class 0 or 1 or 2 or 3 or 4 or 5. For example, if you're asked to classify, I don't know, dogs versus cats versus monkeys versus horses versus whatever, then you'll have basically that many classes of objects, correct, that you're doing in classification. That's good? Okay. So now let's see here. Thank you. These are some examples. I think we've kind of talked about positive sentiment, negative sentiment on tweets, whether the page is relevant or not relevant, whether a tumor is malignant or not malignant, whether the person with the Fitbit is walking or not walking, correct? Those are all examples of binary classifications. Now, here's another example of a binary classification. You've got all of these digits, and you want to predict whether you have a 2 or not a 2. In that case, you've got all of these indicating at yes 2, and all of these as no 2, and that's a binary classification, where the negative would be not 2, and 2 would be the positive, correct? So sometimes you could take a multi-classification problem, convert it into binary classification, and then maybe use all of these classifiers to predict what it is that you want to do, okay? So that's an example of a binary classification. Let's see here. So now, what tools do we have? I'm going to look at the most basic tool that you probably have been introduced in your data science class, which is called nearest neighbor. Okay? The idea behind the nearest neighbor is that you don't really have a model. You have the data. When the new data points come, you predict what it is by looking at what's closest to it. So let's say that I've got all of these classes, and I get myself this new data point, and I'm going to make it big. Comes right there. Okay? And so the question is, what's the class of this? Is it green, is it blue, or is it red? And so what you do is you take this and compare it by some sort of a measure of distance to every data point, all of these data points. And you find the closest. Now you might say, what does closest mean? And that means how you define your measure of comparison, correct? You find the closest to that data point, and you'd say, well, you know what? The class of this is going to be blue because that's closest to this. And boom, you've got yourself nearest neighbor. Now, nearest neighbor is very, very, very overfitting because it's basically finding the best data point and fitting it to that, correct? To kind of control that bias variance, you have what's referred to as k nearest neighbor, where instead of looking at the closest, you look at k closest. So for example, if you look at 3 closest, you would look at those 3, and as a result, you predict the majority, which would be red, correct? So you'd say the class of this new data point is red because 2 out of the 3 is red, okay? And when you do this, you could actually identify what's referred to as decision boundaries. So if a data point appears in here, any data points that's on this side of the line, any data point on this side of the line is going to be classified as red. Any data point on this side of the line is classified as blue. Then we say this here is referred to as the decision boundary. That's where 0 and 1s or negative and positives break. Okay? And it gives you a measure of the quality of the classifier. Now down here is examples of when you go with different values of k. That's k equals to 1. That's k equals to 3. That's k equals to 31. And as you go from 1 to 31, you're regularizing your model. Because if you take k to be all the data samples, then you're getting the average class of all the data samples, basically maximum class with the maximum samples. Okay? You guys are following this? So bias versus variance. Okay? Now, so that's your k nearest neighbor, pretty straightforward. The measure of distance, if you're looking at actually real values and comparing them, you could use Euclidean distance, basically square of the difference of every dimension between 2 points, and then take the square root of that. That's the distance. And for example, if x1 is at 1, 2, 3, x2 is at 2, 1, 0, then it would be 1 minus 2 squared, 2 minus 1 squared, 3 minus 0 squared. Sum of all of those, square root of that, that would be the distance. That's called the Euclidean distance. If you've got, on the other hand, things that are not numeric, for example, if you want to compare these two strings to see how close they are, you could just basically compare letter by letter. And in this case, these are the same with every letter except for the S and P. So that distance is 1. This is referred to as a Hamming distance. Okay? This one and this one, drastic versus plastic, has a Hamming distance of 4 because the two strings differ in 4 locations. And same goes with binary or numeric or whatever. Correct? You guys are following this? It's called Hamming distance. Again, distance is how you measure how close things are. Correct? And then you use that to do your k-nearest neighbor. Now, here's a quote. If you want to actually do it in Python using scikit-learn, you just bring in k-nearest classifier. You give it number of neighbors. So this is nearest neighbor. And then you train it, you fit it like everything else, and then you could make predictions. And with n equal to 1, you get this. With n equal to 5, you get this. And you could try this out on your own. Okay, pretty easy to build with the scikit-learn. Here's what happens when you take this data set and you use n equal to 1. If you look, it basically follows the path of decision exactly and includes every data points. If you say n equal to 10, it kind of smooths things out, and it's going to miss some classes, but the curve is a little bit more, has less variance. Okay? And same goes with the other one. Now, some odd things happen. Like in this case, when k became large, it tried to extend, and it felt like these would be, that finger would be the form of the boundary. Okay? Now, some advantages. It's very simple to understand and implement. You don't need to do much. You just simply compare a whole bunch of points, find out either average of those that are closest to you or majority vote of those that are closest to you if you've got regression or classification. Do not require any training, so training time is 0. You just save the data. But, and works well with low dimensional problems. Really work well just with that. The problem is the classification cost is very high, because although it doesn't cost at all to train, you're not building a model, but if you get a new data point, you have to compare it with all the other data points, and that's a pretty expensive cost, depending on what size you have. So if you've got small data sets, that's fine. That's not a problem. Okay? And then you have to identify k, which is not that big of a deal, because we do that with all the other hyperparameters. Right? All right, so very basic approach to classification. Now, next we want to look at logistic regression. Now, logistic regression, I want to first say it, the word regression in this is misleading. Logistic regression means I'm using linear regression, but I'm also applying logistic function to make it a classifier. So logistic regression is a classification tool, not a regression tool. Unfortunately, the term is confusing. A lot of people confuse that. Okay, so just however you want to remember this, logistic regression is a classification. But it's kind of a very cool way of doing things. The other thing about it, if somebody told you, what is logistic regression? The answer is that it's actually a linear classifier. What that really means? It means that, so pay attention, you remember what was decision boundaries? Where 1 and 0 on a binary classification is separated? Logistic regression has only a line that separates that decision. Okay? So that if you looked at logistic regression, the way it works, let me just go back here and do, if I were to do logistic regression on this, what you're going to see is you're going to see that you're going to get this as your decision boundary or this as your decision boundary, because it doesn't have flexibility to form these circles or these other boundaries. And if your data is not linearly separable, means that you can't draw a line and separate your yays and nays, then you won't get a good solution. Are you guys following this? Now, how does it work? It actually works pretty cool, because you could use the same gradient descent tools that we've talked about for regression on logistic regression, basic classification. Okay. So what you do is, if you think of it, remember your h before was what? The h before was x dot w plus b. Remember that? You took your x values, multiplied by w's, and then added the bias to it, correct? That was for regression. To make it a classification, all you have to do is kind of force it to make a separation of values. So you take this and put it inside of another function, which is called the logistic function, also referred to as the sigmoid function. Okay, so the two are the same. Logistic function and sigmoid function. Okay, so I want you to pay a little, because this is something that we're going to see over and over and over, so I want you guys to get a good feel for it. Okay, so if you look at the logistic function, basically input to it is z, or whatever you want to call it. So basically this is the logistic function, which is 1 over 1 plus e to the power minus z. You could give it whatever z is. So z can go from minus infinity to infinity. But if you look at it, what is g sub z? Well, think of it. If z is infinity, correct? If z is very large, what is e to the power of minus z? 0, correct? 1 over would be very small, correct? 0. So you're going to get 1 over 1 plus 0, which is 1, correct? So as z increases, this thing saturates at 1. Now, what about if z is really low, say minus a million? E to the power of minus million is e to the power of a million, which would be very large, correct? 1 over 1 plus a very large number is very large number. 1 over that is 0. It approaches to 0, correct? So it saturates at 0. And if z is 0, what is e to the power of 0? 1. Anything to the power of 0 is 1, correct? 1 plus 1 is 2. 1 over 2 is 0.5 or 0.5. So when you look at this function, you'd see that with z values of 0, it is right here. With z values of 2, it's already gotten there. And minus 2, it's already gotten there. That's 2 and minus 2. And with z values of 8, we are already saturated right here. So that's z of 8. And anything after that, it's saturated at 1 and minus 1. Now, this is referred to as sigmoid function or logistic function. And you will see later on when we talk about neural network, this was something that have been used for a long time. And later on, we learned that was not the best function to use. Okay, so now let's take a look at this and see what does this mean with respect to everything we've talked about. Basically, we take our old h values. Our old h values were what? Our old h values were x dot w plus b right here. And we apply the logistic functions to that. So basically, what our linear regression model gave me, I squash it, force it to go to 1 or 0. And therefore, I make a classification. The closer you are to 1, the closer you are, the more the confidence you have in the positive class, the closer you are on 0. So you could think of that as probabilities, correct? So 0.9 means a very high probability of being right there at the target 1, correct? You guys are following with me? Okay, so, and therefore, this becomes the squashing, forcing our old stuff to now be either 1 or 0. And in here, we hope that we get out of this region when we go through the process of gradient descent. Are you guys good? This is basically our linear region we refer to. Okay, moving on. So now, how do you compute costs? Now, you could use mean squared error as cost, like we have done before, correct? You might remember how we compute cost, J. The problem with that, because we have applied this nonlinearity, this sigmoid, if you use the old cost, your cost function is no longer convex. It's going to have a whole bunch of valleys and makes it more difficult to kind of get there, okay? And with a linear model, you don't want to have any of that nonlinearity, okay? So the cost actually is called cross entropy cost, which is a new term for you guys, and you should remember it because it comes our way quite a lot. So cross entropy cost, and it looks like this. It looks ugly, but it's not really. If you could think of it, you only have two classes, correct? Y, what are Y values? Y values can be either 0 or 1, correct? You guys are with me here, correct? So what this is doing is saying, if Y is 0, so let's see, Y is 0, this becomes a 0, this becomes 1 minus 0, so it only leads to this term, correct? That's if Y equals to 0. You guys following this? If Y equals to 1, basically 1 minus 1 is 0, minus 1 times this is that, and that would become this term. The negative is used because you will see soon the log of fractions is negative. So we want to convert them into positive, correct? Log of fractions negative. Okay, so now let's spend some time looking at that. And so you see, this is the sum of that cross entropy error over all the samples, like before, correct? And divided by the number of samples, correct? So let's look at that for one sample, correct? So I'm going to just look at one sample, and I'm going to write this down here. Please pay attention. I think you're going to see what this actually means. Insert a blank page. So we're saying cost of a single sample, little j of little sample, would be basically y minus y log of h minus 1 minus y times log of 1 minus h. Okay? So first we're going to focus on y equal to 0. That means my class is negative. And if y equals to 0, then j is equal to minus log of 1 minus h. And then we're going to look at y equals to 1, which basically means j is equal to, because if y is 1, this part goes to 0, I'll get minus log of h. Okay? So now, you guys remember your log function? If I drew this, if this was, say, h, and if I say this is log of h, you guys remember how it worked? So basically, when h was 0, when h was 1, log of h was 0, correct? Log of 1 is 0, correct? You guys following this? And then anything less than 1, it would be negative, correct? So it would be this, and then as it gets close to 0, it will become infinity, correct? It goes up. And then as it goes above it, it would look like this, correct? You guys are with me here? Now our worry is not up here. So up here, we don't care. Why don't we care about this area? Why? Because h is a class label, which we just saw that the sigmoid squashes it between 0 and 1, correct? So h will never get above 1. So that's the region that is of interest to us. So far, so good? You guys are with me here? So now let's negate this. So let's do minus log of h. So I'm going to use a different color. So minus log of h. So minus log of h would basically reverse this up, correct? So it brings me like this. You guys good? Following this? Just flip it up. So now, having this, let's take a look. So when y is equal to 1, I'm focusing on this right now. When y is equal to 1, j is minus log of h, correct? So what happens if h equals to 0? What's minus log of h? What's j? When h goes to 0, this thing becomes infinity, correct? Very large. J approaches infinity. Okay, you guys with me here? As h gets closer to 0. Okay? As h gets to 1, what happens to j? J gets close to 0, correct? You guys are following this? So what does this tell you? It tells you that if y is 1 and if h is 1, your cost is 0. If y is 1, your h is 0, your cost is infinity. Because your prediction, 0, is different from the actual 1, therefore you have a large cost. You see how it's giving you back that? So basically what this equation does, it either gives you a very large cost or it gives you 0 cost. It would give you 0 cost if the 2 labels match. It would give you a 1 cost if the 2 labels don't match. And then if you look at the other side where y is equal to, so if you look at this case, what really is going to happen is we're going to flip things around. So instead of, let me use a different color. So instead of this coming this way, it actually ends up going like that. Because I have 1 minus h. When h is 0, this becomes 1. When h is 1, this becomes 0. It flips things around. And as a result, what you're going to see is that for this case, you're going to see when h is equal to 0, j equals to 1. When h is equal to 1, j becomes closer to infinity. Again, this is for y equal to 0. So 0, 0 gives you a low cost. Sorry, 0. It gives you a low cost. H equal to 1 gives you a high cost. When the 2 labels don't match, you get a high cost for both cases of y of 1 and y of 0. And that's referred to as cross entropy. Okay? And that's the measure we're going to use with this, and later on you'll see with our other classifications. Okay? My time is up. We'll come back here and we'll spend some more time looking at this and take it from here. See you guys on Thursday. Have a nice Wednesday.